Yeah, it's visible.
Yeah. Okay, thank you. Okay, so thanks, Trish, for the kind introduction, and I'm sorry I'm not there with you in person. I wish I could stand just about right where Trish was standing a moment ago. Yeah, I'm still thinking about what the person before me said, and of course, despite the um, circumstances in the little bubble of mathematicians, you still have our Indian hosts who are citing Hungarian poets. So, maybe all hope is not lost with mankind. Yeah. Anyway, so start my course. Of course, this is going to be a little bit
Sorry, before you start,
impromptu because
sorry, before you start,
the
could you slide your camera to it's blocking the top right corner slightly. Is it?
sorry.
Oh, you need to move your own. Well, yeah. Can you just move it? Maybe I think you can just move it around the corner of your screen.
Maybe I'm not completely understanding what you mean. So, what's the matter?
Pierre, hello, Pierre, do you hear me?
Yeah.
One is that, this little icon like containing your own.
Oh, this one.
Yeah, if you can just,
Okay, is that better?
Perfect.
It's all right. Yeah, I have two screens to manage in my head, so that's a lot. Okay, so right, so this is going to be a little bit impromptu, so I'll still try to make it worth your while. And of course, I welcome questions, and I guess you just interrupt if you have one. Yeah. Okay, so there's 4 lectures, and this first one is going to be a little bit introductory, and then we'll do some stuff in the subsequent ones. All right, so let me start with something which is maybe a bit more familiar to most of the audience. So this is Bernoulli percolation. And so in Bernoulli percolation, you have a graph. So say the triangular lattice, like that I denote by T, and here's a little piece of it. And in percolation, you have a parameter P, which you can vary, and you open sites individually with probability P. Okay, so this is site percolation on the triangular lattice, and on the right, all the sites are colored blue and red, depending on whether they're open or closed. Okay, and famously in percolation, you ask about whether or not you have an infinite component of, say, open vertices. And so I've chosen this, triangular lattice setup because this is actually the setup in which we can say most things in low dimension. And so one theorem is this. So if you take this model and you choose the density P equals a half, then the probability that 0 will be connected to distance r is decaying polynomially. So we might parameterize this as r to the power -1 over rho, which is what physicists would write. So maybe if there is one or two who are in the room, they'll feel a bit more familiar with this parameterization. Okay, and this exponent rho, which people call a critical exponent. So the important thing is that it exists and it happens to be equal to 48/5. Okay, so of course this is the tip of an iceberg, and there's many people who contributed along the way, and I'm just going to highlight a few ingredients that go into this theorem, just in order to contrast them with what's going to be going on later. So, so there's maybe at least three important pieces that fit together to give you this result. So the first one is that, first of all, where criticality is. So here I chose P equals a half, and and it turns out that this is actually the critical parameter. So this is the threshold P across which an infinite connected component of blue side emerges. Okay, and so this is a theorem by Keston, and it builds on works of others. So I didn't write all the relevant names here. And so this identification of the critical point is actually a symmetry property of the model. And the symmetry I'm alluding to is called planar duality. So I've tried to show you what that means in the picture. So you can actually take your triangular lattice. So that's where the triangular lattice first comes in convenient. And you can draw these little hexagons that I drew in yellow. So this is what's called a dual lattice. And now you see that you basically have a partition of all of your two-dimensional space, and you can give each honeycomb, each hexagon, the color of the vertex it contains. So I guess the two bottom ones are going to be colored blue, and the upper one is going to be red. And then instead of thinking about vertices, you can think about a path of hexagons. And so, for instance, one thing you can now exploit is the fact that, if you take, say, a large rhombus, then, whether or not you will ever either have a horizontal path of, blue rhombi or a vertical path of red ones, but you won't have both. And, at p equals a half, these two probabilities are actually equal, and so that's where you see that at 1/2, you start to have macroscopic crossings with non-degenerate probability, and so this is the first inkling of the fact that 1/2 is the critical probability. Okay, so there is a strong symmetry property that goes into figuring out where the critical point sits. Okay, that's the first ingredient. And then, the next ingredient is essentially if you assume that this model has what's called a conformally invariant scaling limit. So what this means is that you should now think of the mesh size of your triangular lattice as being not equal to 1, but rather equal to delta, and you send delta to 0, then actually at this critical point p equals a half, the clusters of blues and reds, they will be non-degenerate in the limit. So for instance, what the theorem tells you is that, a critical percolation cluster is something which is actually not quite two-dimensional, right? It's maybe 2 minus 1 over rho dimensional. So it's actually pretty bulky. The Hausdorff dimension is close to 2. But it's still something which is neither microscopically small nor macroscopically large. And so if you assume that you have a limiting object, a limiting cluster, and that it's invariant in law under conformal transformations, then actually there's a classification result that tells you, all of the clusters that you can produce this way. So actually, the classification is rather of the boundary of these clusters, and they are instances of what are called Schramm-Loewe evolutions. So this is a classification of basically all, random conformally invariant curves that have a Markov property. And then there's one that sort of stands out for percolation. So this is where the choice of the parameter comes in, because the exploration path and percolation is depends only on what happens locally around you, and the only local SLE is the one where kappa is equal to 6. Okay, so if you assume that you have the scaling limit, then and you can classify the limiting objects, so it's lots of this. But then if you're clever like these guys, then you can basically do computations in the continuum to determine various things, and among them this exponent rho. Okay, and then of course the missing ingredient is to actually prove this convergence, and that's what Smirnov did. So he proved how these formula, and so he was looking at certain crossing probabilities, and maybe the most important thing about Cauchy's formula is perhaps not the formula itself, but in fact, I never remember exactly what it says, but what's important is that it's actually a formula which describes the limit of some connection probability, and this formula is conformally invariant, so that that furnishes, so to speak, the missing ingredient. Okay, so so when you put all this together, then you get something like this theorem. So there's of course much more to be said. So first of all, let me briefly mention. So usually, one mentions this one-arm exponent in conjunction with another. Traditionally, and this goes back to work on Keston, together with what's called the four-arm exponent, which is related to pivotal points, and you can think of this as saying something about the derivative of this one-arm probability. And okay, once you can prove something like what I wrote here about the scaling relation, about this derivative, and you prove certain scaling relations, which is something that Keston had already done earlier, then basically you can access all the critical exponents, or almost all the critical exponents that that are related to this model. Okay, so just to show you, I mean, all of these references are already more than 20 years old, but this is still actually a very active field of research. So, for instance, these little O of ones errors. So actually, I think the one that's in the first theorem I wrote, to my knowledge, still stands. I'm actually not entirely sure what's the best available result there. But there's, for instance, the question about whether these errors can be improved. And for instance, in the half-plane case, they can be much improved. So you can look at this recent reference here and the references therein if you're interested in the state of affairs there. And so another thing is that, I chose this triangular lattice in the previous slide. Actually, you could also look at bond percolation on the square lattice, which has the merit of also having its critical point sitting at 1/2 because you have planar duality as well. And so there, the results are not quite as advanced yet. So for instance, the theorem I showed you, we don't know how to prove it, and the problem is the third ingredient. So we don't know how to prove conformal invariance, but there's partial progress. For instance, this reference that I mentioned, which shows rotational invariance. Okay, and even in the world of two-dimensional critical phenomena, I mean, so I focused here on percolation because that's what I want to talk about in this course. But there's of course also the Ising model, and in fact, one of the mini courses, the one by Dima Chelkak, is going to be very much on matters related to this conformal invariance properties for the Ising model, if I'm well informed. Okay, so this is two-dimensional percolation, side percolation on the triangular lattice and related models. And so if you humor me, maybe let's just try and think of this in a slightly different way, which is going to make the next step perhaps a little bit more accessible and intuitive. So just imagine that you take your triangular lattice and you stick a little spin on top of every side of the triangular lattice. So you can imagine that it goes vertically. And the spin that you put at each vertex x is just a random variable phi x, which is a standard Gaussian. And you choose these standard Gaussians completely independently. Okay, so so phi x is independent of phi y whenever x is not equal to y. So you can think of this, if you like, as a sort of discrete white noise field. Okay, and so if you do this, then you can rephrase percolation in a slightly different way, but I like to think of this picture, so that's why I'm showing it to you. So you can think of percolation as essentially a landscape. Okay, so now I've sort of drawn my graph horizontally. It's here. Okay, so this is my triangular lattice. And I drew this continuous yellow curve, but of course it's only a bunch of discrete points. Okay, so you have these field variables sitting at every vertex of your graph. And now you can just think of, instead of, changing the parameter P, you vary sort of the sea level A. And you look at the vertices where, phi x is bigger than A. Okay, so you see that whenever your yellow point is above this barrier here, actually you're open, and when your phi is below the value A, then you're actually closed, and you have these clusters that form in this way. So all I'm doing here is really I'm coupling the percolation configurations as P varies, same probability space. So traditionally this is done using uniform random variables, but here I just choose to do it with Gaussians. Okay, why not? And so in this picture, another way that you can think of it is you can think of A as being the sea level, and then you have this sort of yellow landscape, two-dimensional landscape, and you basically flood it with water up to level A, and the open clusters are the mountaintops in this landscape. Okay, and now PC equals a half, and this reparametrization just amounts to saying that the critical height AC is equal to 0. Okay, and so the reason why I'm describing the model in this way is that, of course, now you can think about varying the landscape. So here, the case of Bernoulli is the choice of a completely decorrelated landscape, but there are other choices. And that's basically going to be the backbone of this mini course. Okay, I'm just going to pause for a moment if there are any questions until here.
Any questions on the Zoom as well?
Yeah, I can't see the chat. I'm afraid. Yeah.
So I think the AV team can see the chat, but maybe before we move on, Pierre, would you? So we can't see you at all now. Do you reckon you can just show your face slightly? Yeah. I think if you slide it all the way up, covering. Honestly, I think that's fine. So let's just leave it like that. So no questions in the audience. No questions on the Zoom. No questions on the YouTube. Okay. Yeah, go for it.
So I think actually the picture is never going to stand in the way of anything I write on the slides. So maybe it's just going to be fine with a little snapshot in the corner. I can always get rid of it. I mean, whatever. Yeah. Okay. Okay. So I want to now change this landscape, which will give rise to different percolation models. And so I'm not going to choose just any landscape. I'm going to choose one very specific one. And as the mini course unfolds, I will highlight multiple times why this choice presents certain advantages that other choices do not. But let me, before we go there, let me just stress that, I mean, there is in principle absolutely no limitation to your imagination as to how you can choose phi. And I think maybe the bottom line of many of the things I am going to say is that this flexibility in the choice of phi can lead to other models which have sort of rich, structure and can actually be investigated rigorously. And so, there's room there to, and there are quite possibly other choices of phi which people haven't discovered yet that that could be actually tractable. So of course, the caveat here is, I mean, this is also what I was trying to highlight with the example of the Bernoulli percolation, side percolation on the triangular lattice, is that you see, in some sense, for mathematicians, I mean, part of the game is, of course, to identify models in which you can actually write a theorem. I mean, of course, we all believe that if you take, this model here, Bernoulli side percolation on the triangular lattice, and you modify the model a little bit, so maybe the phi x depends a little bit on what happens in its local neighborhood. It's not completely independent of say phi at its neighbors. Then you would still see the same phase transition with the same critical exponents. But of course, proving this is apparently, I mean, we haven't succeeded. It's difficult, even if you change the lattice a little bit. So the story with the square lattice, where you keep 2 out of the 3 ingredients that you needed for the proof. I mean, the third one, as of now, we don't know how to make it work. Okay, so yeah, so all of this to say that it's also our duty as mathematicians to try and find the models which actually have some features that make them tractable. Okay, and here I'm going to make one choice which actually does that. Okay, so let me formulate this a little bit more generally, also because we're going to go away from sort of the two-dimensional world, which is part of the motivation. So imagine you have a graph. It could even be weighted, but I'm not going to introduce that. It's just additional baggage to carry on. Okay, and so you imagine that, say, maybe the graph is infinite, so it has an infinite vertex set and is connected for the purposes of studying percolation. And now on this graph, you have what's called the random walk. So this is just the usual, say, discrete time Markov chain X, which, if at time n, xn is equal to x, then it's going to pick neighbor uniformly at random. So I guess in my picture, X has 1, 2, 3, 4 neighbors. So it picks one uniformly at random, say this neighbor Y, and then it jumps to Y. So xn plus 1 will be equal to Y. And then, it forgets everything and repeats this procedure. That's the usual random walk on the graph. Okay, and I'm going to assume that my graph is transient, which means that, with probability 1, the trajectory of X eventually escapes to infinity. So in particular, the graph cannot have a finite vertex set for this to be true. And so it's going to be convenient to phrase this in terms of what's called the Green's function of the random walk, which is this quantity g of xy, which is going to pop up all the time. And so this is just the expected number of visits of this random walk at the vertex y if I start the random walk at x. Okay, so px here is the law of my random walk with starting point x. That's this little subscript here. And if you Fubini these two measures, then you can also write this as the expected number of visits at y, which is maybe more intuitive. Okay, and so saying that the graph is transient in one of several equivalent definitions is just saying that this Green's function, say on the diagonal, is transient. Okay, and is finite, and in fact, if that's true, then it will be always finite. Okay, so that's the random walk on the graph. It's a very natural and simple probabilistic object that you can associate to a graph, and in fact that you can use to study various geometric properties of the graph. Okay, and so the landscape that I want to introduce is what's called the Gaussian free field. So this is now, again, as in the previous slide, a random field. So you think of phi x as being, a little spin that lives atop the vertex x. And this GFF, so it's a Gaussian field. So it means that any finite linear combinations of these phi x as a Gaussian random variable. In particular, each phi x is a Gaussian random variable, and as you know, if you have Gaussians, then the law is completely specified by the first and second moment, as you can just see by looking at the Laplace transform or the characteristic function. And so here, my fields are always going to have mean 0, so expectation is 0. And so then I need to specify the second moment, so this covariance expectation of phi x times phi y. And I choose it, so that defines the Gaussian free field really, to be the Green's function. Whoops, that was unintended. I choose it to be the Green's function of this simple random walk. Okay, and so this choice here is a little bit ad hoc when you see it for the first time, but it's actually extremely important. I mean, there's essentially a one-to-one correspondence between properties of the random walk over here that translate into properties of the Gaussian free field, and one important one is a Markov property, to which I'll come back later. Okay, so of course this is infinite dimensional. My vertex set is infinite, but the way you should think of it, and you can make this rigorous by having finite volume approximation of the field, say with zero boundary condition, is to if there were a Lebesgue measure in infinite dimensions, then the density of my Gaussian free field would be what I've written at the bottom here. And the reason why I'm mentioning this is that here you see a little bit what this field is doing. So you see there's, in some sense, a penalization, which is, so you are somehow diminishing the probability of configurations where this sorry. You are diminishing the probability of configurations where the quantity in this exponential gets large. And so in particular, you are penalizing large values of these increments or these discrete gradients, as you could think of them, in your graph. Okay, so I guess these gradients being constrained, you should think of as making the field actually relatively stiff. So if at a point x my field has value phi x, then at its neighbors y, the value of the field is not going to be all that different, because if it's very, very different, then I'm going to pay a lot in this exponential. So this is a way to think about it, which is a little bit dangerous sometimes, because it can lead to somehow wrong intuition. But actually, especially in transient setups, this is actually not a bad picture to have in mind. Okay, so this is basically the landscape that we're going to use. And so if you think of this in simple examples, so maybe the simplest example is if you take Z3, so the usual cubic lattice. And of course, I'm taking the dimension to be at least 3 because I want my random walk to be transient. So dimension 2 is sort of out of the question in some sense. So then this green function decays like distance to the power 2 minus d, so it decays polynomially. And this exponent 2 minus d, you should think of it as being relatively small. So these correlations are actually relatively strong. It's what people call a strongly correlated field. And in particular, it's very, very different from this completely uncorrelated discrete white noise that I used to model Bernoulli percolation in the slide before. And so you do expect that using this landscape will actually lead to critical phenomena which will have different exponents than those that you would see if you were doing Bernoulli percolation on the same graph. Okay, so good. So I have my Gaussian free field, I have my transient graph, and now I can define the percolation model that I want to tell you about in this introductory talk. So I'm going to use my landscape now to define a percolation model. And again, I have my C level, my control parameter, which plays the role of P, and I'm calling it A. So here it is. And so the way I choose to open and close edges is maybe going to be not the naivest way that you could do things. And I'm going to come back to what the naivest way is, but I guess in the second lecture. So again, this is in some sense a choice of model, which is maybe, not the first one that comes to your mind in the same way as in Bernoulli percolation, it's probably more intuitive to study bond percolation on the square lattice than side percolation on the triangular one. But it just so happens that on the triangular one, there's you can prove more things, at least as of now. And so here the simplest way I know to obtain a theorem that looks a little bit like what I showed you before, and in fact the only way as of now, is to define a bond percolation model. So it's not going to be a side percolation model. And the way you open or close an edge is according to the following procedure. So imagine that you have your edge xy, and you sample your Gaussian free field everywhere on your graph. So in particular, phi x and phi y. And now you say, okay, given my Gaussian free field, I open an edge or I close it. So say I open it independently, given the field, with probability what I wrote here, 1 minus the exponential of minus phi x minus a positive part times phi y minus a positive part. Okay, so this is an idea that goes back to Lupu, and I'll say a little bit more later on. So here you see, in order to open the edge, you need the thing in the exponential not to be 0. So in particular, you need phi x to be bigger than a and phi y to be bigger than a. So you want to be, you have my C level a, and you want the field to be above a. But even when that's the case, there is still a non-zero probability that you might still close the edge. Okay, so that's a choice, and I'll explain what motivates this choice later on. Okay, so for now, let me just state a theorem. So take, for instance, ZD, and you take D greater or equal to 3, and you choose this, this C level, this control parameter A, which plays the role of P. You choose it to be 0. So this is very similar to what we were doing with P equals a half moments ago. And now the theorem is that, so actually you do have an exponent in this model. The one-arm probability at this critical point a equals 0 decays polynomially. So again, formally it's the same statement. And here the exponent is 2 over d minus 2, maximum a half. So actually in dimension, if you unpack this maximum in dimension 3, it's equal to 2. In dimension 4, it's equal to 1. In dimension 5, it's equal to something. And then when you hit dimension 6, then the two quantities are equal. And, from dimension 6 onwards, it stays constant, equals to 1/2. So, and this rho equals 1/2. So this probability decaying like r to the minus 2 is exactly what you have in the mean field regime in percolation in high dimension. So it's actually mean field from above dimension 6. Okay, so this is actually a very recent result, and there's a number of people who contributed to it. So let me briefly mention all the relevant contributions. So in the form I've stated the theorem here, it was first proved in dimension 3 by Ding and Wirth, actually with a better error than a little O of 1. So the lower bound was without the little O of 1, and the upper bound, maybe the little O of 1 was, I guess, maybe log R over log R or something like that. Okay, so then in dimension 4, it was proved by Dritz, Prévost, myself, and dimension 5 by Ding. So this is more recent works. and in dimension 6 and higher, so there was a paper of Werner which actually started all of this, which was about dimension 7 and higher, and then Saidin picked up on that. So that's the first paper from 22, and then more recently at the upper critical dimension, they were able to prove this as well. And so in dimension 7 and higher, so this is where the first 22 paper is, and also the one by Wendelin. This you should think of as being in the spirit of what Eisenman and Newman did in Bernoulli percolation in some time ago. Okay, and actually we know more than this. So we have actually up to constant bounds in low dimension. So that means the probability on the left hand side is bounded by from below and above by constant times r to the minus 1 over rho. And so in dimension 3, this is again the DPR gang, and then in dimensions 4 and 5, this was proved afterwards by Tsai and Ding, and actually their proof also works in dimension 3. Okay, so this is all relatively recent stuff. So I want to spend, so I still have a little bit of time. Do I? How long do I have? 5 minutes or something?
Oh, you have 15 because we started 10 minutes late.
Okay, perfect. All right, so I want to give you some analogies to these ingredients that I mentioned for the two-dimensional result, just to sort of contrast things a little bit. So I told you one important thing in the dimension 2 case was sort of topology that you can exploit using planar duality, and that was the story that you can either have horizontal or open or dual closed crossings, but you cannot have them simultaneously. So actually, maybe I should have drawn a rhombus here, but indulge me, or think of bond percolation, if you will. And so you need something that replaces this, something that's going to allow you to identify the critical point, which here was a equals 0, if you remember, still in say dimension 3, and there the replacement for that. So all of this is very loose, and of course part of the purpose of the mini course is going to be to show you these things. So here actually what you exploit is actually something rather probabilistic, which is that you can identify the clusters in the model I just defined as actually being clusters of what are called Brownian loops. So you should think of them, of these clusters, as being formed out of a bunch of Poisson loops that you throw in your graph in a natural way, and clusters are formed by loops that intersect. And what happens is that, so in low dimension, for instance, in dimension 3, the clusters that are big in your percolation model at at the critical value equals 0 happen to be exactly the clusters that also contain macroscopic loops at in your box. So so this equality is actually not a trivial statement. I mean, one inclusion is obvious. If you have a macroscopic loop, then you are a macroscopic cluster, but the opposite is far from trivial, and it actually defines low dimensions in a sense. But so the point for the purposes of this introduction is just for you to think that actually you should think of clusters at the critical point as being clusters that contain in dimension 3 macroscopic loops, and a piece of a loop, you can think of it as being essentially a piece of a random walk. And so then that implies that your clusters, because you have pieces of random walks in them, they're at least two-dimensional objects. And so if you have two of them, then 2 plus 2 equals 4, and if they're sort of in generic position, then they will have to intersect. So this is what my little picture down there, with the two sheets intersecting is supposed to suggest. Of course, the clusters themselves look nothing like a plane, but they are two, more. I mean, they have dimension exceeding two by the reasoning I just outlined. And so this is how you can actually, make them essentially merge into one. Okay, but of course this exploits in a fundamental way this property that you can identify your clusters as being clusters in a Brownian loop soup, and this Brownian loop soup idea is something that goes back to a paper of Lauder and Werner from some time ago. Okay, so that's one thing. And so the other thing was, when you remember the duality was to actually identify, first of all, where your critical point sits. And then, there was the story with computing rho. And so, in 2D, this goes by, you first prove that you have a scaling limit, and then you do some smart computation and the scaling limit, and that gives you access to rho. And here the story is actually a little different. I mean, it's maybe more in spirit to what happens with easing in dimension 2, and that is that it's rather in some sense a model which has some integrability. So you can actually perform computations directly at the discrete level for the specific percolation model that I define. And just to give you a sort of an idea about this, so if you look at this probability to open an edge when a is equal to 0, so this is this 1 minus x of minus phi x phi y that I wrote here. So think of phi x and phi y as being positive. So this is actually the probability that a Brownian bridge, on an interval, say of length 1, to make things simple. It's not exactly that, but let's not delve into this. Stays above the barrier a equals 0. And so this is, of course, this is actually the reason why you choose these probabilities in this way. And this was, Lupu's initial observation that actually, so he didn't phrase it like this, he phrased it in the language of loop soups, but it's equivalent. So basically what this model that I defined is doing is it's looking at percolation of excursion sets of the Gaussian free field on an extension of your graph where you add these continuous line segments. So you can actually extend the free field, which is defined on the vertices, to a free field that lives on this metric graph structure. And all you have to do, that's just the Markov property, is you sample the discrete one and you connect the discrete field values phi x, phi y by independent Brownian bridges. And the probability I gave you is just a probability that, everywhere along this cable between x and y, the field stays above whatever value a you choose. So really, you're just studying excursion sets of the free field on this metric graph structure. And so the reason I mentioned this is that you can now use this to explore clusters. I mean, for instance, if your point, let's say 0, and you want to explore the cluster above level 0 around you, then you can do so in a continuous way. I mean, you can really stop when you hit the value 0. And this Markov property is extremely important. I mean, it's one of the, I've already mentioned it, and I'll mention it multiple times. This is one of the of the integrable features of the model, so to speak. And I mean, let me just note that in the two-dimensional world, of course, the Markov property plays also a very important role, right? I mean, in this classification theorem, the defining properties of these SLE curves are, on the one hand, conformal invariance, and on the other is this Markov property as well. So somehow the Markov property is in one way or another intimately linked to all the models that we can I mean, almost or many models that we can analyze in percolation. And I think maybe one of the reasons is because it marries well with the exploration of clusters. So I'll say more about this during the lectures. Now, just to conclude, let me just mention that this is actually all part of a more general story. So I focused on the case of ZD and this theorem, but actually the sort of bigger picture is the following. So you can, for instance, consider graphs which have natural properties from the point of view of the random walk. And so two natural properties are those that I'm mentioning here. So imagine that balls in your graph grow like r to some power alpha, and that the Green's function decays to zero, sort of polynomially in the distance between points with another exponent, which I parameterize by beta minus alpha. So maybe the example to keep in mind is this box on the right-hand side. So on ZD, you would take alpha to be D, and you would take beta, which is the walk dimension, to be 2. And so then the conjecture is that, if you're in low dimensions, which presumably means that alpha is less than or equal to 3 beta, then actually all the exponents are rational functions of these two numbers, alpha and beta alone. So here in the table I'm showing to you, you see the values are given in terms of alpha and another parameter nu, and nu is just alpha minus beta. So it's just written in a different way. Okay, and so this conjecture, maybe if you want to be a little cautious, you should also assume that your graph satisfies some ellipticity condition, but that's maybe a technical point. The ellipticity refers to the random walk. But okay, let me not get into this. Okay, and so in fact, you can.
Oh, sorry, Pierre, you're cutting out. Can you just repeat that?
You hear me now?
I think so. Can you say something?
Yeah.
Oh, yeah, we can hear you now. Sorry, can you say that after ignore the issue of ellipticity?
Don't think much. But anyway.
Yeah, it's yeah, I don't know if it's on our end or your end. Maybe the AV team can say. It's not. So Pierre, I think there might be. Is there a connection issue?
Oh, hear you a bit.
It keeps cutting out, like in every. Maybe try turning your video off to see whether it's a streaming issue.
Oh.
I think unfortunately it's still cutting out. Just
So
maybe.
my next slide is thank you. So we can leave it at that.
Yeah. Well. Okay. Fantastic. Hear us okay? By the way.
Sorry.
Can you hear us okay?
Yeah. Right now I can't, but before I could.
Okay. So I'm not. Yeah. Now we can hear you. So hopefully it equilibrates. Anyway. So yeah. So let's thank Pierre for the first lecture. So are there any questions from the in-person? Please don't be shy. Oh, yeah, okay. One second.
Hello. Yeah, you mentioned this SLE connection. Are you going to discuss where the value 6 comes from? Or it's not going to be relevant for your discussion?
So the value
R equal to 6, where does it come from? Are you going to discuss it or it is not?
what I can tell you is where it comes from.
Sorry, Pierre, the connections are just cutting out. I don't know what's the best thing to do. Maybe we postpone questions to your second lecture, or also, I guess, Subhajit and maybe Franco can answer some of these questions, right? Or I don't know. Do you think that's a reasonable compromise?
Sure.
Okay, yeah. Yeah, but I think it's worth yeah. So sorry Pierre about the technical difficulties at the end, but thank you, and so see you in a few hours after lunch.
Yeah. Okay, thank you.
Thanks. So okay, so to the online people and to the people in person, if you want, we could try doing the questions to Subhajit and Franco. Otherwise, please hold your questions to after lunch. By the way, for lunch, remember to bring these. Otherwise, I'm pointing at the cards. Otherwise, you might not get free lunch. And it's upstairs in the cafeteria. So we'll see you all at 2:15 for Pierre's second lecture. Hopefully, there'll be the technical issues will flatten. Okay, sorry, Pierre, and thank you so much.